Margaret, my 14-year-old daughter, enjoys collecting her thoughts at breakfast by reading the Merriam-Webster's 360-word calendar. On June 15, 2001, a page from that calendar appeared on my coffee machine telling me that perspicacious is an adjective meaning of acute mental vision or discernment, keen. It continued, as you can see, Pierre de Fermat's last theorem stymied great mathematical minds for 350 years until perspicacious British mathematician Andrew Wiles devised a proof in 1993. We shall hear more about that at our dinner meeting in the National Building Museum this evening. Now, anyone in Webster's dictionary requires no special introduction at all. But he is a very special person, so let me add, Andrew Wiles is probably the world's best-known mathematician. Among many other honors, he was knighted in the year 2000 at the tender age of 47. The CMI interviewed Andrew during our Millennium meeting 1 year ago in Paris. He made a wonderful comment about the soul of mathematics. Let me quote, "We, mathematicians, feel a part of an enterprise that's been going on for a long time and will go on, we believe, forever. Countries come and go. Political systems come and go. But somehow, mathematics seems to have a permanence that nothing else has." It's my tremendous pleasure and honor to introduce my friend and perspicacious mathematician, Andrew Wiles.
Thank you. It's my great pleasure to welcome the Olympiad contestants, their parents, organizers, and others to the closing ceremony of this Olympiad. I'm going to address myself primarily to the contestants, the aspiring young mathematicians, in what, for some of you at least, may be the graduation from high school mathematics. Unlike a traditional graduation, perhaps many of you will have no clear idea of what awaits you in the outside world of professional mathematics. However, before I talk of the future, let me first congratulate you all. Some have arrived here by overcoming immense personal difficulties. Others have arrived here overcoming only immense mathematical difficulties. But all of you have shown great talent and a real capacity for tremendous hard work. Let me then welcome you also, not only to this event, but also to the greater world of mathematics in what many of us believe is now a golden age. However, let me also warn you. Whatever the route you have taken so far, the real challenges of mathematics are still before you, and I hope to give you a glimpse of this. What then distinguishes the mathematics we professional mathematicians do from the mathematical problems you have faced in the last week? The two principal differences, I believe, are in scale and of novelty. First, of scale. In a mathematics contest such as the one you have entered, you are competing against time and against each other. While there have been periods, notably in the 13th, 14th, 15th centuries, when mathematicians would engage in duels between each other. Nowadays, this is not the custom. In fact, time is very much on your side. However, the transition from a sprint to a marathon requires a new kind of stamina and a profoundly different test of character. We admire someone who can win a gold medal in 5 successive Olympics, not so much for the raw talent as for the strength of will and determination to pursue a goal over such a sustained period of time. Real mathematical theorems will require the same stamina, whether you measure the effort in months or in years. You can forget the idea, if you ever had it, that all you require is a bit of natural genius and that you can wait for inspiration to strike. There is simply no substitute for hard work and perseverance. The second principal difference is one of novelty. It often comes as a surprise to non-mathematicians that we do place such a strong emphasis on originality. One common reaction is that mathematics has all been known for years. All we do is to perform calculations. This could not be further from the truth. Firstly, there are many problems, old and new, that have not been solved. Secondly, the creation of new mathematics enables us to dramatically simplify and clarify the old results. Calculus is now routinely taught in high school. However, in the 17th century, it could not have been understood except by the very, very few eminent mathematicians in the world. This is not because people are smarter now, but because our language is clearer. The language of mathematics has been purified by the many new uses to which it has been put. Let me stress that creating new mathematics is a quite different occupation to solving problems in a contest. Why is this? Because you don't know for sure what you are trying to prove, or indeed whether it is true. It is amazing how much difference it makes to know that a problem can be solved. And even if you believe, as I do, that most reasonably asked problems, mathematical problems at least, can be solved, it may be that you live in the wrong century. Some problems solved in the 20th century could not conceivably have been solved in any previous century. Simply too much new mathematics had to be developed. What do you need to deal with this? You need the wisdom to choose problems that can be solved and the faith to trust in that judgment when it seems hopeless. I've been speaking perhaps as a pure mathematician. But mathematics is, of course, also the language of science and the language of technology. The demands in these directions may perhaps seem different, but I suspect that the profound contributions in these areas require the same blend of talent, hard work, and perseverance. I've talked now enough in the abstract. Let me talk about one of these unsolved problems. I'm going to talk about a problem that is at least 1,000 years old, perhaps more. It is a part of one of the 7 problems selected by the Clay Mathematical Institute as its Millennium Prize problems. For each of these, as you heard before, there is a prize of $1 million. But I'm getting ahead of myself. Let me begin with the prehistory of this problem. You'll see here, written in clear text, a sequence. Could I go back one? That seems to have jumped. Thank you. You see here in ancient cuneiform script mathematical statements that were written down nearly 4,000 years ago. These are preserved on tablets in the University of Columbia's library, and they were deciphered this century, and they describe part of a problem which many of you know, but before you recognize it, perhaps I should give you the translation of what is written in these tablets. These were ancient Babylonian solutions to the equation x squared plus y squared equals z squared. Of course, the familiar one, 3 squared plus 4 squared equals 5 squared, but also many others, reaching what seems the incredibly large 12,709 squared plus 13,500 squared equals 18,541 squared. You may be surprised that these fit on the tablet, but the Babylonians wrote in base 60, and it's much easier to write a large number in base 60. We don't know what uses the Babylonians put such results to. It's always been assumed that the Babylonians only did mathematics for its uses. Why this is assumed, I don't know. It may not be true. These solutions are, of course, related to what we now call Pythagoras' theorem. We think it most unlikely that the Babylonians had proved Pythagoras' theorem. On the other hand, there are many people who think it's unlikely that Pythagoras proved Pythagoras' theorem. So perhaps we should not hold that against them. Pythagoras' theorem, of course, says that the square on the hypotenuse, c squared in this picture, is equal to a squared plus b squared, the sum of the squares on the two shorter sides. I believe the first proof is found in Euclid. We do not know for sure whether Pythagoras solved this. But what we do know is that the Greek period marked a crucial transition from examining special cases and algorithms to the axiomatic method and to the unifying concept of proofs. This idea of proving theorems rather than doing calculations, as I have said, is the bread and butter of modern mathematics, even though some rather provocative observers believe that this era is now ending and that we will be replaced by machines. Well, what does this have to do with the problem I was going to explain? The problem I'm going to explain, which, as I said, can be viewed as part of one of the Clay Mathematical Institute problems, is the following. Suppose we take such a right-angled triangle. We know from Pythagoras' theorem that a squared plus b squared equals c squared. The question is, if you pick an integer n, does there exist such a right-angled triangle where the lengths of the sides, a, b, and c, are all rational numbers and the area is n? This problem has a long history. We can date it back at least to Arab manuscripts of the 10th century. Perhaps it goes back to the Greeks. We don't know. Fibonacci was challenged to give an answer for n equals 5 in the court of Frederick II, and he achieved it. He then gave an incorrect proof for the case n equals 1, and it was in fact Fermat who wrote down the first correct proof for the case n equals 1, That is, he showed that there is no right-angled triangle with area 1 whose sides are rational. Fermat's margin had room for this one. In fact, it was probably the only complete proof he really wrote out, though there were one or two sketches of others. Well, in principle, it seems at least easy to write down triangles with given area. For example, you can write down a 3, 4, 5 triangle, and the area, being half the base times the height, is 6, so that 6 is the area of a right-angled triangle. These, for historical reasons, have become known as congruent numbers, the ones which are the areas of right-angled triangles. The problem is, how do you decide in general whether an integer n is the area of a right-angled triangle with rational sides? There is no known algorithm. However, in the last 20 years, a truly remarkable conjecture has been developed which will give an answer to this question. So the question, when does n occur as the area of a right-angled triangle with rational length sides? The conjectured answer for n odd is yes, if and only if the number of solutions to the equation 2x squared plus 4y squared plus y squared plus 8z squared equals n is twice the number of solutions of 2x squared plus y squared plus 32z squared equals n. Although this problem has been around for 1,000 years, it's not surprising that it took almost all those 1,000 years to find such a remarkable conjectural answer. This answer seems to come completely from the blue. And although both the statement and the hypothetical answer are completely elementary, it seems that the relation between them is extremely deep and sophisticated. Even to make this guess required the development of much of 20th century mathematics. Behind this problem lies a fantastic edifice that is now modern mathematics. Why is this? We don't know. Why do such simple-sounding statements require so much sophistication? We don't know. We believe that this is correct. And as I say, it is one case, but it will be a crucial case in one of the Clay Mathematical Institute problems. Let me show you how it works. It's very simple, then, to make these calculations. To find the solutions of 2x squared plus y squared plus 8z squared equals n, for example, take n equals 11. There are 10 solutions, and they're listed there. You take the number of solutions for 2x squared plus y squared plus 32z squared equals n, and again, they are listed there. Equals 11. There are 10 solutions to the first and 4 to the second. 10 is not twice times 4, so there is no solution. If, as in the cases of 5 and 7, the number of solutions to the first equation is twice the number for the second, then there is a right-angled triangle. So this gives an elementary and seemingly miraculous prescription for deciding the answer. Now, I'm not saying that the answer to this riddle will change the world. It will not. But this problem expresses, for some of us, the magic of mathematics, that these strange interrelations between numbers can be studied and solved using the most sustained and wonderful arguments in modern mathematics. The modern mathematics we use to develop these problems, to solve these problems, is itself extremely useful and has been applied in many contexts. Supposing you solve this problem, you still have the question, can you find the right-angled triangle with that given area? It turns out that even if you could solve this problem, it's not obvious what the answer to that would be. Here, it's perhaps hard to read, but this is actually the smallest solution for a right-angled triangle with area 157. Smallest in the sense the numerator and denominator are the smallest numbers. As you can see, this is not something that is found by trial and error. Nor can it even be found simply using a computer. Behind this incredibly elementary problem that has been around for 1,000 years, there is a very beautiful and very intricate theory of mathematics which involves many of the modern branches: analysis, automorphic forms, algebra, most of the kinds of mathematics you've ever heard of, just to pull out this one solution. And knowing all that mathematics, in fact, finding the solution is not too difficult. While I hope that this challenge and the other challenges which you will understand as you learn more mathematics will inspire you to follow mathematics as a career and to try yourselves your hand at one of these great problems. Thank you.